let's resume here. All right, so like I said, this one little fact is very extendable. We can kind of expand factorial as much as needed. Let's do that with this example down below here. N minus 1 factorial over n plus 1 factorial. Can we reduce this? The question is, can we reduce this to an expression involving maybe no factorials, a completely algebraic expression? I'm going to record this lesson for my third period because they're all going to be at the MC. See how this goes. So what's your inclination here? I mean, this n plus 1 factorial I'm looking at, and it can be expanded in the following way, right? Can't it? And maybe that's not fruitful, but we'll try it and see what happens. This is n plus 1 times n factorial, right? The bottom. But we can keep doing this. This is what I'm saying. You can keep expanding this out. N factorial is also n times n plus n minus 1 factorial, right? Are you okay with that? Because then we're just going to cancel that out. You see it? Okay. So this we can write more simply as n times n plus 1 on the bottom, right? An expression that doesn't involve any factorials. Is that okay with you? I hope that makes sense. This is a little easy first case. And then what we'd like to do today then with this only this one piece of technology is to prove some identities, right? And by prove identities, I mean like the kind you did earlier this year with trig identities, right? Except this will be easier because there's only one trick in the book, and that's this one right here. It's not like a whole large array of things you have to memorize in order to get these. It's just this one trick. And there's lots we can ask and do. So for example, let's prove the following identity. So let's start together, and feel free to, on all these today, feel free to race ahead, please. It's a great mathematical instinct to beat your teacher to the punch of what I want you all to be. What do we first want to do? Well, we first want to all, hopefully, the first thing you want to do is you all want to recognize what these things mean. Those are combinations, and you know, hopefully by heart, what those combinations are. The definition of that is, right? So what would that first one be? It'd be n plus 1. And by the way, I guess we should start and say, which side do you want to start on, right? I think it's pretty obvious we want to start on the left-hand side, but we should have that conversation on these problems as well. So we'll start with the left-hand side, which is n plus 1, choose 2, minus n, choose 2. And we'll see if we can manipulate this. Just the left-hand side. Remember how all of our logical conversation about how to proceed logically in a proof applies right now, just like it did when we were doing trig proofs. So we want to manipulate this side until it looks like the other side. We'd love this to just come out to be this bang. Those who are racing ahead, are you already seeing it? Did you already get it? Okay, so this is n plus 1 factorial. This is the definition of n plus 1, choose 2, over 2 factorial times n plus 1 minus 2 factorial. Right? Isn't that the definition of combination? Likewise over here, n choose 2 will be n factorial over 2 factorial times n minus 2 factorial. Let's proceed. What do we have? N plus 1, we'll just clean this up a little, that first one up, over, and actually maybe we should start expanding it out right now, just for fun. N plus 1 factorial is n plus 1 times n times n minus 1 factorial, and we can stop whenever we like. Why am I stopping there, though? Because on the bottom we have n minus 1 factorial, right? And on the top, over here, how far do we want to extend? Well, we got n times n minus 1 times n minus 2 factorial. Is that okay? All over 2 times n minus 2 factorial. Notice I've dropped the factorial on both of the 2's. You see why the 2 factorial is just 2. Okay, and then that's the hard part. If there's a hard part here, that's maybe the hard part. is to see why I did what I just did. Do you see why I did what I just did and that I'm allowed to do it? At any time, you can expand an n plus 1 factorial, this first one here we're looking at here, into, instead, n plus 1 times n minus 1 times n minus 2 times n minus 3, etc., right? So that's what this says, and this just says etc., right? But why did I decide to expand it twice? Well, because this is nicely going to cancel out the denominator. Likewise over here, why did I choose to write n factorial as this big guy? N times n minus 1 times n minus 2 factorial. Well, because it's going to cancel out the bottom. Are you seeing it? So stop whenever you like, whenever it serves your purpose. All right, because this is the fun part, right? And then the rest is just, algebraic manipulation. What do we have up here? N squared plus n over 2. And over here we have n squared minus n over 2. If we're careful, we subtract here, we get n squared minus n squared. Well, here, we'll do it nicely. Minus n squared plus n all over 2. Is it there? Boom, boom. These go away. And we get 2n over 2, which is n, which is what we wanted to show, right? If you like, you can go back and put a QED, or you can put a black box, whatever, something that says we're done. Does that make sense? This is exactly what we wanted to show. And then, of course, as usual, we want to step back and appreciate the beauty of this problem for what it is, right? Cool. That's amazing that that's true. We should also say that. Okay, how about this one? I don't mean this one actually to be like any harder, really. So just try it as a practice. I'll give you a second to get it, and when you get it, you'll know you got it because you got it. I'm going to check. I don't need to come around and check your answer. You'll feel the euphoria for yourself. Proceed like the last one. Good practice with algebraic manipulation. If you get it, you can shout Eureka. Or hooray. Get it? gets expanded into, that's an n.
What is that? Oh, is it?
Yeah.
Right there. Yeah. Yeah, it is. Sorry. Okay.
You see it?
Oh.
Very satisfying, right? Yeah.
So it's not like you have to go in sequence or anything. Like if you're trying to cancel out n minus 2 and the denominator, you don't have to like use n minus 1 and like n minus. Is that
Oh, yeah, you mean like do it in 2 steps?
like you don't have to add all the like ones that are in between.
I mean, you can just, I'm trying to think what you're trying to say. You mean like, do we need to separate this into, what are you saying?
Okay, so like like
Kind of like an accordion. You can like expand it out until necessary, until you find something useful that can cancel out, right?
But when you're expanding out, you can't just leave out terms in the middle. Like you can't jump from n plus 1 to.
I mean, no, that wouldn't be true then anymore, right?
Okay.
You know, it'd be like saying, can I write 6 factorial as 6 times 4 factorial? No, it's 6 times 5 times 4 factorial, right? You can't miss the 5 in there because it would be wrong, right? Yeah. So it works out and wonderful and it feels good. And I think you'll find again tonight as you do some of these that these are you know, surprisingly delightful and therapeutic. Really, you know, it's a fun process to prove these. Okay, let's see if we can do 2 more here. I think we have enough time. We gotta throw some R ones in here. This one's almost immediate, so this is gonna take you hopefully like almost as soon as you write it down, you'll be done, right? There's not really much more to do here, maybe 1 step. But this is us proving what? I mean, haven't we already intuitively understood this result right here? Look at it for a second and see what it says. Haven't we already understood this? That n choose R, like 5 choose 3 is the same as 5 choose 2. That's what this is saying, isn't it? So let's prove it once for all symbolically, just so that we can convince ourselves. Because we think it's true, but let's make sure we know it's true. Yeah, exactly. We've already kind of proved it intuitively, haven't we? Exactly. Yeah. Yeah, and I don't know. I mean, we could make that a little more rigorous and have that be our proof too. But this is a good way to prove it too, and it's easy. So I might start with the right hand side. Just I don't know, picking the side here. So choose n minus r is n factorial over n minus r factorial times n minus r factorial, which is n factorial over n minus r factorial times, what's that? R factorial, and that is n choose r. QED. Yeah? Is that okay? I mean, like I said, I don't have much more to say there. But I think it's worth saying at least once here that this is in fact true. Okay. In fact, many of these are motivated by our intuition. This one too, actually. I'll tell you what it means after we do it, okay? But there's a nice intuitive explanation for why this works. But this is a tricky one. We're gonna have to, I'm gonna try and fit this on the board, but this is actually a little bit long. I think this will take us a little bit of work to get. But this is what we'll do for like the remainder of the class. There's one problem, because this is tricky enough that it'll take that much time. Before we get too involved, I think we're all convinced just by looking at this that we want to work with the left-hand side, right? I mean, just because they're 2 big combination things, right? So I think we're right to do that. But before we get too involved in this and invested in the problem, let's just off to the side here, say what the right-hand side is. Just so we know what it is, when we see it, we'll know what we have, okay? What is this over here? It'd be n plus 1 factorial over r plus 1 factorial times n plus 1 minus r plus 1 factorial. Right? And then we can think even more thoughts about this if we like. That thing in the bottom is n minus r factorial. Okay, so there's a thought. within a thought. Okay. Okay, so that's where we're going, right? And you remember one of our tips when we were proving identities with trig, same here too, is to keep the target expression in mind, right? Because otherwise we're going to be like aimlessly moving around over here, right? So we want to eventually have this side, as we work with it, look like that expression. Really? Ooh, okay. Let's see if we can do it. So I'm going to work with the left-hand side, and again, as always, feel free to race ahead. N minus r, I like that. That's nice and simple. And choose r plus 1. What do we get here? We have n factorial over, this one's nice, r factorial, n minus r factorial.
Whoa,
Plus.
I thought our factorial, I've seen that somewhere.
Yeah, maybe that'll be convenient in the end. That'd be great. Over r plus 1 factorial times n minus r plus 1 factorial. Okay, let's stop and breathe for a second. Everyone good? Yes? I mean, we haven't done much yet at all, really. We've just written out what those combinations really mean. And now our task is an algebraic one. Manipulate this stuff to look like this. Can we do it? Yeah, you know, I would love, because, for a couple reasons, I would love to combine these two fractions somehow. Yes? Do you agree? Furthermore, I think I already have a good idea about what I should have the common denominator be. I think I'd like to, for two reasons, right? So I think I'd like the common denominator to be, listen carefully, r plus 1 factorial times n minus r factorial. Do you see why? Because this has an n minus r factorial, and it almost has an r plus 1 factorial. Do you see it? Not quite. This over here has an r plus 1 factorial, and it almost has an n minus r factorial. Once we simplify this, you'll see. Okay. So that's one motivation. The other motivation is, why did I say that denominator? It's also the denominator up here, n plus 1 factorial times r n minus r factorial. So do you see, like, even before I've done a single thing on this, I'm already kind of thinking, okay, I think I'm going to be able to get a common denominator. And I think it's going to be really great, okay? And once we do, maybe we'll be done. That'd be great. Okay, so in order to make that common denominator happen, and by the way, a little magic eraser here, if you don't mind. Is this okay? Boom, boom, boom. Is it okay? We're okay with that. All right. Just make my life a little bit simpler. How do I make this be that denominator? R plus, like I said, the denominator up here is going to be r plus 1 factorial times n minus r factorial. Okay, this is our LCD. R plus 1 factorial n minus r factorial. So this already has this. How do we make it? How do we make the r plus 1 factorial up here? Yeah, we just need to multiply this by r plus 1, don't we? This denominator, and of course the numerator as well. So let's do that. So we get r plus 1 times n factorial over r plus 1 times r factorial n minus r factorial. So if at any point you don't like what we just did, you can cancel out r plus 1, okay? And over here, it's a little bit harder to see. We've already got the r plus 1 factorial. We're loving it. But we need an n minus r factorial. Well, what is this, and why did I say that this is close to what we need, this n minus r minus 1? Yeah, what do we need to multiply by here? Yeah, just n minus r over n minus r, right? So here, I'll write this way. N minus r. Okay, is that okay? I'm introducing it in the middle here, just for whatever reason, right? Just to make it look nice.
Oh, I see it.
You see it all the way to the end? Okay, you could cancel this n minus r out if you wanted, and we've had what we had before. I'm sticking it in the middle to make it obvious what we're about to do, right? Do you see it? So up on top here, I'm just going to leave that as is, r plus 1 times n factorial. And then here's the big move. This is why we did what we just did. This is r plus 1 factorial times n minus r factorial. And this over here, this is n factorial times n minus r. We'll leave that as it is. And then the denominator, we have r plus 1 factorial times, are you tracking? Is that true? Is that really n minus r factorial? Okay. This is going back to the definition, right? we started with today. Like I said, only one trick in the book here today, but it's deep and far-reaching, isn't it? We can use it for a lot of cool stuff. All right, now we can finally add these fractions. Here we go. So we get r plus 1 times n factorial plus n minus r times n factorial, all over our common denominator, r plus 1 factorial, n minus r factorial. Moving over in this direction. And again, we can kind of cheat, can't we? Because we have the end expression in mind. We already know that in like 2 steps from now, we better be here up at this expression, you know, the thing that we have on the right side. So even if you didn't have that in mind, you would factor out an n factorial because you have that irresistible urge.
And what is that for me too?
I know. RMBC, sorry. But we've got to just nail this one out here. All right, here we go. And then, yeah, what is that on the top? This is just n factorial times r's go away, n plus 1, which is just, is that what we want? Yeah, that's n plus 1. I wrote it in an unfortunate order, right? But if you wrote it as n plus 1 times n factorial, it'd be obvious that that is, in fact, n plus 1 factorial on top over r plus 1 factorial times n minus r factorial, which is what we want. N plus 1, choose r plus 1. Okay, so that's about as complicated as these get. And just because I have, this is more important than RMBC, let me say this one last thing, okay? If you have Pascal's triangle, okay, what is this actually saying? N choose R is one of these things right here, right? All of these is like an N choose R, right? So like say we're right here, that's N choose R, say. Then what does N choose R plus 1 mean? We're still in the same row, N, but we're at the next door. And what happens when we add these two? This is saying when we add 2 elements of Pascal's triangle, we get the next row element R plus 1, right? So there's a nice, very visual proof of this too, and that's this plus this equals this, right? Done.
We just like draw the
No.
Pascal's triangle.
Thanks for asking. No, it's good to do this like once in your life, at least. But you might also come up with crazier identities from this then too. You might be like, okay, well that should be true that that this plus this equals this, right? Because these 2 things combined to get that. This plus this equals this, right? You could come up with some other cool things in Pascal's triangle. Anyway. There you go. Okay. Homework. You'll be well equipped to do homework 5 tonight. Plus, I have some more practice on binomial stuff.